Subscribe to our channel, and hit the bell icon, to never miss a video from us.
Hi everyone, and welcome back to this course on Selenium. In previous lesson, we had an introduction to Selenium, its tools and component, and also how it works. In this lesson, we will learn about Selenium Web Driver, and how to start with it. We will take a detailed look into Selenium Web Driver, its elements, action APIs, and also learn about Remote Web Driver. Then we will move on to Selenium Grid in our next lesson.
WebDriver drives a browser natively, as a user would, either locally, or on a remote machine, using the Selenium server. Selenium WebDriver refers to both the language bindings and the implementations of the individual browser controlling code. This is commonly referred to as just WebDriver. WebDriver is designed as a simple and more concise programming interface. WebDriver is a compact object-oriented API. It drives the browser effectively. Selenium supports automation of all the major browsers in the market through the use of WebDriver. WebDriver is an API and protocol that defines a language-neutral interface for controlling the behavior of web browsers. Each browser is backed by a specific WebDriver implementation, called a driver. The driver is the component responsible for delegating down to the browser, and handles communication to and from Selenium and the browser. This separation is part of a conscious effort to have browser vendors take responsibility for the implementation for their browsers. Selenium makes use of these third-party drivers where possible, but also provides its own drivers maintained by the project, for the cases when this is not a reality. The Selenium framework ties all of these pieces together through a user-facing interface that enables the different browser backends to be used transparently, enabling cross-browser and cross-platform automation. Selenium Setup is quite different from the setup of other commercial tools. Before you can start writing Selenium code, you have to install the language bindings libraries for your language of choice, the browser you want to use, and the driver for that browser. You can install the Selenium IDE from the link provided here. First of all, you need to install the Selenium bindings for your automation project. The installation process for libraries depends on the language you choose to use. You can check the Selenium downloads page to make sure you are using the latest version. Let us see some examples of installing Selenium bindings. 1. Java. Installation of Selenium libraries for Java is accomplished using a build tool. You can see all available versions on Maven repository on this link. For Maven, add the Selenium Java dependency in your project, pom.xml file. And for Gradle, add the Selenium Java dependency in your project, build.gradle file. Installation of Selenium libraries for Python can be done using pip. Installation of Selenium libraries for C# can be done using NuGet, in one of two ways. Installation of Selenium libraries for JavaScript can be done using npm. Installation of Selenium libraries for Ruby can be done using gem. Next, you need to install the browser drivers. Through WebDriver, Selenium supports all major browsers. WebDriver drives the browser using the browser's built-in support for automation. Since all the driver implementations are provided by the browser vendors themselves, they are not included in the standard Selenium distribution. Let us now see how to open and close a browser with Selenium. Once you have a Selenium library installed, and your desired browser driver, you can start and stop a session with a browser. Typically, browsers are started with specific options that describe which capabilities the browser must support, and how the browser should behave during the session. Some capabilities are shared by all browsers, and some will be specific to the browser being used. Here we will look at examples of starting a browser with the default capabilities. We will look at the examples related to Chrome browser. Make sure that the version of the Chrome browser and the version of Chrome driver must match. For Java, you can use the following code. For Python you can use the following code. For C#, use the following code. For Ruby, use the following code. And for JavaScript, you can use the following code. And for Kotlin, use the following code. Let's write our first Selenium script. Everything Selenium does is send the browser commands to do something or send requests for information. Most of what you'll do with Selenium is a combination of these basic commands. First will be, start the session. To start the session in Java, we use the following code. To start the session in Python, we use following code. For C#, we use the following code. For Ruby, following code is used. For JavaScript, we use following code. And to start the session using Kotlin, we use the following code. Next, we will take action on browser. In this example, we will navigate to a web page. For Java, we use the following code. For Python, we use following code. For C#, we use the following code. For Ruby, following code is used. For JavaScript, we use following code. And for Kotlin, we use the following code. In our next step, we will request browser information. You can request a bunch of types of information about the browser, including window handles, browser size, position, cookies, alerts, etc. For Java, we use the following code. For Python, we use following code. For C#, we use the following code. For Ruby, following code is used. For JavaScript, we use following code. And for Kotlin, we use the following code. In our next step, we will establish waiting strategy. Synchronizing the code with the current state of the browser is one of the biggest challenges with Selenium, and doing it well is an advanced topic. Essentially, you want to make sure that the element is on the page before you attempt to locate it, and the element is in an interactable state before you attempt to interact with it. An implicit wait is rarely the best solution, but it's the easiest to demonstrate here, so we'll use it as a placeholder. For Java, we use the following code. For Python, we use following code. For C#, we use the following code. For Ruby, following code is used. For JavaScript, we use following code. And for Kotlin, we use the following code. Next step is finding an element. The majority of commands in most Selenium sessions are element-related, and you can't interact with one without first finding an element. To find an element using Java, we use the following code. To find an element using Python, we use following code. For C#, we use the following code. For Ruby, following code is used. To find an element using JavaScript, we use following code. And for Kotlin, we use the following code. In the next step, we will take action on element. There are only a handful of actions to take on an element, but you will use them frequently. To take action on an element using Java, we use the following code. To take action on an element using Python, we use following code. For C#, we use the following code. For Ruby, following code is used. To take action on an element using JavaScript, we use following code. And for Kotlin, we use the following code. In the next step, we will request element information. Elements store a lot of information that can be requested. Notice that we need to relocate the search box, because the DOM has changed since we first located it. To request element information using Java, we use the following code. To request element information using Python, we use following code. To request element information using C#, we use the following code. For Ruby, following code is used. To request element information using JavaScript, we use following code. And for Kotlin, we use the following code. Now, we will end the driver process, which by default closes the browser as well. No more commands can be sent to this driver instance. For Java, we use the following code. For Python, we use following code. For C#, we use the following code. For Ruby, following code is used. For JavaScript, we use following code. And for Kotlin, we use the following code. You can combine these 8 steps into a complete script, with assertions, that can be executed by a test runner. Let's take a look at some commands for browsers. To get the current page title from the browser, follow these commands. And if you want to read the current URL from the browser's address bar, follow these commands. To open your website, use the following code. And for pressing the browser's back button, use following code. For pressing the browser's forward button, use the following code. Web elements. The majority of Selenium code involves working with web elements. 1. Locator Strategies. A locator is a way to identify elements on a page. It is the argument passed to the finding element methods. Selenium provides support for these 8 traditional location strategies in WebDriver. Selenium 4 has relative locators. These locators are helpful when it is not easy to construct a locator for the desired element, but easy to describe where the element is, in relation to an element that does have an easily constructed locator. Relative locator methods can take as the argument for the point of origin, either a previously located element reference, or another locator. For example, consider this image. If the email text field element is not easily identifiable for some reason, but the password text field element is, we can locate the text field element, using the fact that it is an input element above the password element. Similarly, we have below, left of, right of, and near relative locators. Interacting with web elements. Following are the basic commands that can be executed on an element. First is click, which applies to any element. The element click command is executed on the center of the element. If the center of the element is obscured for some reason, Selenium will return an element click intercepted error. Second is send keys, which only applies to text fields and content editable elements. The element send keys command types the provided keys into an editable element. Typically, this means an element is an input element of a form with a text type or an element with a content editable attribute. If it is not editable, an invalid element state error is returned. Third, clear, it only applies to text fields and content editable elements. The element clear command resets the content of an element. This requires an element to be editable and resettable. Typically, this means an element is an input element of a form with a text type or an element with a content editable attribute. If these conditions are not met, an invalid element state error is returned. And fourth is select, which is used for list elements. Information about web elements. There are a number of details you can query about a specific element. 1. Is displayed. This method is used to check if the connected element is displayed on a web page. Returns a Boolean value, true if the connected element is displayed in the current browsing context, else returns false. 2. Is enabled. This method is used to check if the connected element is enabled or disabled on a web page. Returns a Boolean value, true if the connected element is enabled in the current browsing context, else returns false. 3. Is selected. This method determines if the referenced element is selected or not. This method is widely used on checkboxes, radio buttons, input elements, and option elements. Returns a Boolean value, true if referenced element is selected in the current browsing context, else returns false. 4. Tag name. It is used to fetch the tag name of the referenced element which has the focus in the current browsing context. 5. Size and position. It is used to fetch the dimensions and coordinates of the referenced element. 6. Get CSS value. Retrieves the value of specified computed style property of an element in the current browsing context. 7. Text content. Retrieves the rendered text of the specified element. Let us talk about Remote WebDriver. You can use WebDriver remotely, the same way you would use it locally. The primary difference is that a remote WebDriver needs to be configured, so that it can run your tests on a separate machine. A remote WebDriver is composed of 2 pieces, a client and a server. The client is your WebDriver test, and the server is simply a Java servlet, which can be hosted in any modern JEE app server. To run a remote WebDriver client, we first need to connect to the remote WebDriver. We do this by pointing the URL to the address of the server running our tests. In order to customize our configuration, we set desired capabilities.
Let's look at an example, where we want to instantiate a remote WebDriver object, pointing to our remote web server, www.example.com, running our tests on Firefox. For Java, we can use the following code. For Python, we can use following code. For C#, use the following code. For Ruby, use the following code. For JavaScript, use the following code. And for Kotlin, we can use the following code. And to further customize our test configuration, we can add other desired capabilities. Let's take a look at those. 1. Browser options. Suppose you wanted to run Chrome on Windows XP, using Chrome version 67. For Java, we can use the following code. For Python, we can use following code. For C#, use the following code. For Ruby, use the following code. For JavaScript, use the following code. And for Kotlin, we can use the following code. 2. Local file detector. The local file detector allows the transfer of files from the client machine to the remote server. For example, if a test needs to upload a file to a web application, a remote web driver can automatically transfer the file from the local machine to the remote web server during runtime. This allows the file to be uploaded from the remote machine running the test. The local file detector is not enabled by default, and can be enabled in the following way. For Java, use the following code. For Python, we can use following code. For C#, use the following code. For Ruby, use the following code. For JavaScript, use the following code. And for Kotlin, we can use the following code. In addition to the high-level element interactions, the Actions API provides granular control over exactly what designated input devices can do. Selenium provides an interface for 3 kinds of input sources. A key input for keyboard devices, a pointer input for a mouse, pen or touch devices, and wheel inputs for scroll wheel devices, introduced in Selenium 4.2. Selenium allows you to construct individual action commands assigned to specific inputs and chain them together and call the associated perform method to execute them all at once. In the move from the legacy JSON wire protocol to the new W3C WebDriver protocol, the low-level building blocks of actions became especially detailed. It is extremely powerful, but each input device has a number of ways to use it, and if you need to manage more than one device, you are responsible for ensuring proper synchronization between them. Thankfully, you likely do not need to learn how to use the low-level commands directly, since almost everything you might want to do has been given a convenience method that combines the lower-level commands for you. Pointer movements and wheel scrolling allow the user to set a duration for the action, but sometimes you just need to wait a beat between actions for things to work correctly. An important thing to note is that the driver remembers the state of all the input items throughout a session. Even if you create a new instance of an actions class, the depressed keys and the location of the pointer will be in whatever state a previously performed action left them. There is a special method to release all currently depressed keys and pointer buttons. This method is implemented differently in each of the languages because it does not get executed with a perform method. 1. Keyboard actions. There are only 2 actions that can be accomplished with a keyboard: pressing down on a key, and releasing a pressed key. In addition to supporting ASCII characters, each keyboard key has a representation that can be pressed or released in designated sequences. In addition to the keys represented by regular Unicode, Unicode values have been assigned to other keyboard keys for use with Selenium. Each language has its own way to reference these keys. The full list can be found on the link provided here. Send keys is a convenience method in the Actions API that combines key down and key up commands in one action. Executing this command differs slightly from using the element method, but primarily this gets used when needing to type multiple characters in the middle of other actions. 2. Mouse actions. There are only 3 actions that can be accomplished with a mouse: pressing down on a button, releasing a pressed button, and moving the mouse. Selenium provides convenience methods that combine these actions in the most common ways. Click and hold method combines moving the mouse to the center of an element with pressing the left mouse button. This is useful for focusing a specific element. Click and release method combines moving to the center of an element with pressing and releasing the left mouse button. This is otherwise known as clicking. Alternate button clicks. There are a total of 5 defined buttons for a mouse. 0 is left button, the default. 1 is middle button, currently unsupported. 2 is right button. 3 is X1, back, button. 4 is X2, forward, button. Context click. This method combines moving to the center of an element with pressing and releasing the right mouse button, button 2. This is otherwise known as right clicking. Backclick. There is no convenience method for this, it is just pressing and releasing mouse button 3. Forward click. There is no convenience method for this, it is just pressing and releasing mouse button 4. Double click. This method combines moving to the center of an element with pressing and releasing the left mouse button twice. Move to element. This method moves the mouse to the in-view center point of the element. This is otherwise known as hovering. Note that the element must be in the viewport or else the command will error. Drag and drop on element. This method firstly performs a click and hold on the source element, moves to the location of the target element and then releases the mouse. 3. Scroll wheel actions. There are 5 scenarios for scrolling on a page. Scroll to element. This is the most common scenario. Unlike traditional click and send keys methods, the actions class does not automatically scroll the target element into view, so this method will need to be used if elements are not already inside the viewport. This method takes a web element as the sole argument. Regardless of whether the element is above or below the current view screen, the viewport will be scrolled so the bottom of the element is at the bottom of the screen. Scroll by given amount. This is the second most common scenario for scrolling. Pass in an delta x and a delta y value for how much to scroll in the right and down directions. Negative values represent left and up, respectively. Scroll from an element by a given amount. This scenario is effectively a combination of the above 2 methods. To execute this, use the scroll from method, which takes 3 arguments. The first represents the origination point, which we designate as the element, and the second 2 are the delta x and delta y values. If the element is out of the viewport, it will be scrolled to the bottom of the screen, then the page will be scrolled by the provided delta x and delta y values. Scroll from an element with an offset. This scenario is used when you need to scroll only a portion of the screen, and it is outside the viewport. Or is inside the viewport and the portion of the screen that must be scrolled is a known offset away from a specific element. This uses the scroll from method again, and in addition to specifying the element, an offset is specified to indicate the origin point of the scroll. The offset is calculated from the center of the provided element. If the element is out of the viewport, it first will be scrolled to the bottom of the screen, then the origin of the scroll will be determined by adding the offset to the coordinates of the center of the element, and finally the page will be scrolled by the provided delta x and delta y values. Note that if the offset from the center of the element falls outside of the viewport, it will result in an exception. Scroll from offset of origin, element, by given amount. The final scenario is used when you need to scroll only a portion of the screen, and it is already inside the viewport. This uses the scroll from method again, but the viewport is designated instead of an element. An offset is specified from the upper left corner of the current viewport. After the origin point is determined, the page will be scrolled by the provided delta x and delta y values. Note that if the offset from the upper left corner of the viewport falls outside of the screen, it will result in an exception.